So, in this particular course on heat treatment and surface hardening, I will be talking about time temperature transformation diagrams and continuously cooled transformation diagrams. But before that, let us briefly review the kinetics of phase transformation that was done in part 1 of this course. And the phase transformations that we are looking at in this particular part of the course is diffusional type of phase transformation, and you can refer to the lectures in part 1 of this course, particularly the lectures under week 5 to week 7 of the part 1 of the course. So, in order to understand what are the transformation diagrams, we need to have a good idea about how diffusional phase transformations take place. And in this review of what we have already done, phase transformations take place through 2 steps: nucleation followed by growth. And let us first quickly review nucleation and the kinetics of nucleation, then we will follow it up with growth and kinetics of growth of the formed nuclei. Now, nucleation could take place in 2 different ways. One way is homogeneous nucleation, and an alternative way of nucleation is heterogeneous. So, what happens? Suppose we have, to start with, we have the alpha phase everywhere, and as we are cooling down the material to a temperature less than the transformation temperature, where the transformation temperature is the transformation of alpha to beta. So, beta starts to form inside alpha, and for its formation to occur, first a nuclei of a certain size beta precipitate will form. If this beta precipitate occurs anywhere, we will call that as homogeneous nucleation. That means it can take place over the entire bulk of the material. An alternative way that a beta precipitate may form could be, for example, on an existing surface, particularly a grain boundary. So, if I have a polycrystalline alpha phase, a beta precipitate may form on the grain boundary. It could form on a grain boundary, it can form where 3 grains meet, that is on a triple point. It could also form on other defects in the material such as dislocations. This way of nucleation is what is called as heterogeneous nucleation, and in this route of nucleation, this is known as homogeneous nucleation. So, we will assume that in the homogeneous case, a spherical nuclei of a certain size given by its radius. In the case of heterogeneous nucleation, this lens shaped nuclei, which is actually nothing but 2 spherical caps that may form. and the radius of the spherical caps is r. And let us now understand what is the change in free energy that is involved when a beta precipitate forms either homogeneously or heterogeneously. What are the various terms that would go into the overall change in free energy? So, let us try and write an expression for change in free energy delta G in the formation of a nuclei of a certain size. So, this change could be looked at as in different components. For example, there is a volume free energy involved where alpha to beta transformation results in the reduction in the free energy. Let us call that as delta GV, multiply it by the volume of the nuclei that is formed. This is a resulting change which would be negative. Then there is a change in free energy as a result of the formation of an alpha beta interface. This would result in a positive change in free energy, and it can be written as the surface area of the nucleus multiplied by the surface energy per unit area of the alpha beta interface termed as gamma sub alpha beta. Thirdly, there may be a volume change that is involved in the formation of beta. For example, if we consider a transformation of face centered cubic iron to body centered cubic iron at temperatures below 910 degrees centigrade, there is a volume expansion going from face centered cubic structure to body centered cubic structure. As a result, there would be a expansion producing a deformation in the surrounding alpha matrix, and that would resist the change. So, this would produce another change in free energy which would also be positive, and we would call that as delta G sub S. The strain energy, the strain that is resulting into the alpha matrix results in a change in free energy delta G sub S multiplied by what is the volume of the nucleus. Now, alpha beta is greater than 0, delta GS is greater than 0, while delta GV is less than 0. Let me write this slightly differently. Let me take the positive or the absolute value of delta GV and put a negative sign to make things very clear that this is a negative term while these two terms are positive. Now, we had done a detailed analysis in the part 1 of this course as to what would be the critical size of the nucleus beyond which the change in free energy would start to reduce. Because when we plot this change in free energy delta GV versus the size of the nucleus, whether it is homogeneously nucleated or heterogeneously nucleated, that change can be shown or illustrated in a graph like this. So, initially at small sizes the change in free energy is positive and it goes through a peak beyond which it starts to reduce, and eventually there is an overall negative change in free energy. This peak in free energy, it occurs at a size which has been called as the critical size R star. and corresponding to this critical size, there is a critical change in free energy delta G star. Critical free energy. We have analyzed this curve in detail in the part 1 of this course, and the critical size of the nucleus is given by 2 times gamma alpha beta, the surface energy of the alpha beta interface, divided by delta GV minus delta GS squared. So, from this it is very clear that if your surface energy of the alpha beta interface is high, your critical size is going to be high. Similarly, if your strain energy is large, then also delta GV minus delta GS will reduce, and as a result the critical size would increase. That means this peak would shift to higher critical sizes. Corresponding to the critical size of the nucleus, the critical free energy delta G star was derived as some constant F times gamma alpha beta cube divided by delta GV minus delta GS square. I made a small mistake in the critical size of the nucleus. There is no square here. So, it is simply 2 gamma alpha beta divided by the absolute value of delta GV minus delta GS. Now, what is this constant F that is there? That constant F depends on what is the shape of the nucleus. In the homogeneous case, if we assume a spherical nucleus, so homogeneous and spherical shape, F is simply 16 pi by 3. In the case of heterogeneous nucleation and lens shape, as I have shown here in this figure, F is 16 pi by 3 multiplied by 2 plus cos theta times 1 minus cos theta square divided by 2, where theta is the contact angle that the nucleus makes with the substrate. So, in this case, for instance, this was the earlier grain boundary, this angle is theta, and what it means is that theta decides the wettability of beta on alpha. So, if theta is 0 degrees, beta completely wets the substrate. If theta is 180 degrees, it does not wet the surface at all. So, if theta is 0 degrees, if we substitute in this expression, F becomes 0. So, if theta is 0 degrees, F is 0, and what it simply means is delta G star goes to 0. So, there is no barrier to nucleation for in such a situation, while for other values of theta there would be some barrier. However, that barrier would be less than in the case of homogeneous nucleation. If we were to compare the barrier to nucleation versus size of the nucleus, if this represents the homogeneous nucleation case, then the barrier to nucleation is delta G star homogeneous. In the case of heterogeneous nucleation, the shape would be something like this with the same critical radius r, while the barrier to nucleation delta G star heterogeneous is less than delta G star homogeneous, and for very small contact angles delta G star heterogeneous becomes very, very small. So, in systems where homogeneous nucleation could be very difficult, in those systems heterogeneous nucleation may be the only choice for the material to transform. Now, this was a brief summary of just the nucleation process. Now, in order to understand the kinetics of phase transformation, we would need to look at what would be the rate at which nucleation would take place. Now, to look at that, let us first understand that for phase transformations to proceed, we must form a stable nucleus. For radius less than r star, the nucleus formed is unstable, and therefore it will tend to dissolve back to the left of this curve. For sizes greater than r star, the nucleus would become stable because it can simply keep adding more atoms and increase in size, and eventually the free energy change would become negative. So we would need to produce a stable nucleus in order for the phase transformation to proceed. At the critical size, a nuclei that is formed is under what we can call as unstable equilibrium. At this unstable equilibrium, the nucleus could either roll back and dissolve, or it could go forward and become stable. Let us understand this process of how a critical size nucleus could become stable. So, for example, we have created a stable nucleus, not a stable nucleus, a critical size nucleus. So, let us say this is a critical size nucleus consisting of some number of atoms. So, critical sized beta nucleus. Surrounding this is alpha. So, the alpha phase is surrounding it. So, all of this is alpha, and for this nucleus to become stable, even if one of the atom from the parent phase alpha jumps across the alpha beta interface, so this is your alpha beta interface. So, even if one atom jumps, the size of the nucleus would become greater than the critical size and the nucleus would become stable. So, now we would like to explore rate of formation of stable nuclei. That is what is going to govern the kinetics of phase transformation. So, rate of formation of stable nuclei, could be understood in the following manner. It will depend on number of atoms that are surrounding the nucleus, the critical size nucleus, number of atoms in the alpha phase. Let that be Ns. All of these atoms are vibrating with a certain frequency called the Debye frequency. Multiplied by that frequency, multiplied by an activation barrier across which a atom from the alpha phase needs to go across the alpha beta interface to the beta nucleus, and that activation barrier is delta GD, the activation energy for the jump. And therefore, the probability of a jump is related to e to power minus delta GD divided by kT, where k is the Boltzmann constant and T is the temperature. All of this put together gives me the rate nu prime at which I would be forming a stable nuclei. Now, number of stable nuclei per unit volume, not rather stable, number of critical sized nuclei per unit volume would be given by n star, and that is equal to n0 e to power minus delta g star divided by kT. So, n star is the number of critical size nuclei in a unit volume, n0 is the number of potential sites where a critical size nuclei can form per unit volume, and delta G star of course is the critical free energy for the critical sized nucleus. So, at any given time I can expect to find so many critical size nuclei per unit volume, out of which some of them would roll forward and become stable, while many others would roll back, become unstable and dissolve back. So, not all of these critical size nuclei will form stable nuclei. At what rate this is going to happen? This is going to happen at a rate of nu prime, and hence the nucleation rate I will call this with the symbol I, number of nuclei, number of stable nuclei per unit time per unit volume of the material. This is simply equal to n star times nu prime, and if I just multiply both of these quantities together, I will end up getting n0 ns nu e to power minus delta G star by kT multiplied by e to power minus delta GD by kT. There will be another quantity that I have to introduce, and let me introduce that quantity called P. P is the absorption probability. That even if an atom jumps, it may not get absorbed in the nucleus, and that jump actually may end up in a failure. Now, this expression gives me the rate of nucleation, whether the nucleation is occurring homogeneously or heterogeneously. Now, in the next lecture, we will briefly analyze the nucleation rate in terms of temperature, how it varies with temperature below the transformation temperature, how I varies as a function of undercooling. Undercooling is undercooling delta T, which is defined as the temperature at which the nucleation is taking place minus the transformation temperature. So, as the undercooling increases, which means the temperature of transformation reduces, how the nucleation kinetics changes, we will analyze in the next lecture.